Hello everyone, in this video we're going to be looking at section 12.1, which is vector valued functions. Subsection 1, we're going to talk about space curves and vector valued functions. Obviously we've got a lot of definitions here, so bear with me. A space curve C is the set of all ordered triples that have f of t, g of t, and h of t as their components, or their x, y, z components, with their defining parametric equations: x equals f of t, y equals g of t, and z equals h of t. Right? So it's just extending everything to the three dimensions here, and we have a parametric equation for the x, the y, and the z. And again, that's where f, g, and h are continuous functions on an interval. Okay, so before we look at examples of space curves, and again, this is just the idea of extending. Before we had like an f of t and a g of t in the 2 dimensions, and now we're going to do it in the 3 dimensions, right? So it's just extending it naturally. But before we jump into that, we're going to look at a new type of function called a vector valued function. This type of function maps real numbers to vectors. So the definition of a vector valued function: a function of the form r of t, and we use this bold-faced r to represent, instead of like f of t, we use r just because that's just common notation, but we use bold-faced to remember that the output is going to be a vector, right? And so what this looks like is I have a function in the I component and a function in the G component, or the J component, or in the 3 dimension I have a function in the I component, a function in the J component, and a function in the H component. So what we're going to do here is we're going to plug in a certain value of t. You'll plug it into the function that is there in the I component, and it will give you a value, which will then become your I value of a vector. And then we'll plug in that same t to the G component, the G function, and we'll get a value, and then that will become the J component of a vector. Right? And so this is a function just like anything. So I plug a bunch of t values, I get a bunch of outputs, but instead of real numbers as outputs, I get vectors as outputs. And just as we can write vectors with I, j, and k notation, we can also write vector valued functions as I, j, and k notation. That's what we do here. And we can represent vectors with the component form, right, with the square brackets, and we can do that just the same for function vector valued functions. All right, so I can also write it, okay, just the I equation there, and the and the J or second component equation there, or for the 3 dimensions. Okay, so we need to make an important distinction between vector valued functions, boldface r of t, and the real valued functions f of t, g of t, and h of t. So the vector valued function, it takes in real numbers as inputs. It takes in t values as inputs. And then what does it output? It outputs I, j, k, right? It outputs a vector, right? The real valued functions, which are f of t, g of t, and h of t, take in real numbers and plug out real numbers, right? And then that real number becomes the component, the I or j component. So vector valued functions serve dual roles in the representation of curves. Vector valued functions really are how we represent curves in the plane. So the first way is by letting the parameter t represent time. You can use vector valued functions to represent motion along a curve. Just like in the example of using the parameter t as time in the 2 dimension, it can represent motion along the plane. Now we can have motion along a curve, right, in 3D space. In the more general case, you can use a vector valued function to trace the graph of a curve. Okay, so we've thrown a lot of stuff at you, but the main point here is this first sentence: in either case, the terminal point of the position vector r of t coincides with the point xy or xyz on the curve given the parametric equations. So essentially what that's saying is that I have a curve in space that's represented, that has t values that I plug in, right? T equals something, something, something. And I can either represent that in 2 ways. That curve can be represented by a vector valued function, or it can be represented by parametric equations. In either case, it's really the same thing, because the parametric equations, if you look back up to our definition up here, right, of a vector valued function, It's not a coincidence that I used f of t here and f of t here, and then g of t here and g of t here, and h of t here and h of t here. Because the idea is if I have a set of parametric equations just like this, then I'm going to plug in a bunch of different t values and get a bunch of different x and y points, right? So it would just be a bunch of x, y, z points, right? I'd have a bunch of different points here on the graph. However, if I plug it into a vector valued function, then I get a bunch of different vectors. But the idea here is in order for a vector valued function to represent a curve in space, is that I'm going to take every vector that I get, right? So for t equals 1, say I get this vector, and then what I'm going to do is just put a point at the terminal point of that vector, right? Every vector in somewhere, right? And that terminal point of every single vector, when I put every vector that comes out of each value of t, I draw the terminal point of it, and then those set of terminal points will represent a curve, right? And it will have an orientation, right? So that's kind of the idea of a vector valued function, is that it can represent points in space, because I can really just put a curve. I can either represent it as a set of parametric equations, or I can represent it as a vector valued function. Okay, and this will probably make a little bit more sense the more we work through it. So the domain of a vector valued function. Unless otherwise stated, the domain of a vector valued function, r of t, is considered to be the intersection of the domains of the component functions f, g, and h. So if we look at this example here, if I want to find the domain of r of t, which is ln of t in the I component plus the square root of 1 minus t in the j component plus tk, well, what I need to find what I need to do is find the domain of each of these component functions, right? Oops, I already did purple. Right. So let's first find the domain of, remember, we typically call f of t the function that corresponds to the I component, which is ln of t, right? And so what is the domain of ln of t? Well, remember that what values can I plug into logarithm? I can't plug in negative numbers, and I can't plug in 0, right? So in other words, I have t greater than 0, strictly greater than 0, because I can't plug it in. In interval notation, this corresponds to parentheses 0 to infinity, right? And so that is my domain of f of t. And now let's look at my domain of g of t, which is just the function in the j component, which is 1 minus t. So remember, what do we need to do in this case? Underneath square roots, we can't have negatives, so I need 1 minus t to be greater than or equal to 0, which means I need t to be greater than, let's try that again, which means I need 1 to be greater than or equal to t. So in other words, t is less than or equal to 1. So in interval notation, that is, negative infinity all the way up to 1, including 1, or bracket. So that is my domain of that function. And now the third one, the domain of h of t, which is the just t. What values am I allowed to plug into the function just f of x equals x, or h of t equals t? Well, I can plug everybody in, right? Nothing bad happens. So that domain is all real numbers. So now in order to find the domain of the entire function, right, the domain of the vector valued function r of t, it is the intersection of all those domains, right? And so the intersection of all these domains would be, let's see, I have to not include 0 and start at 0, and then I go all the way up to 1 and not include 1, right? So that is my domain. Okay, so now let's practice plugging in some values. Evaluate r of t at each given value of t, right? So r of 1, we'll just go to our function and we plug in our vector valued function and we plug in 1. And again, our final answer should be a vector, right? Because this is a vector valued function. So I plug in 1, I get 1/2 times 1 squared I minus 1 minus 1 j. So I get I minus 0j, or in other words, just, not just I, right? We get 1/2 I. So 1/2 I plus 0j minus 0j. So in other words, we get 1/2 I, which is a vector, right? Because this is a vector valued function. Plug in 0. So I go 1/2 0 squared I minus 0 minus 1 j. So I get 0 I minus negative, so plus j. So in other words, I get j, which again is a vector. What about if I plug in s plus 1? Well, again, this just gets treated the same way. I just plug in s plus 1 in for t, so I get 1/2 s plus 1 squared I minus s plus 1 minus 1 j. So I get 1/2 s plus 1 quantity squared I minus s j, which again is just another vector, this time with a different parameter s in there, or a different variable s in there. Okay, so example 3, represent the line segment from P to Q by a vector valued function and by a set of parametric equations. Okay, so it's actually, the first thing we're going to do is find a set of parametric equations to represent the line segment from P to Q. So remember earlier we found, I think it was like 11.5, if we have a point and a vector that a point on the line and a vector that's parallel to the line, then we can write the parametric equations of that line, right, in the 3D. So that's what we're going to do here, is we're going to take one of these points, and then we're going to find the vector that that connects P and Q, right, the vector from PQ, and the vector from PQ is parallel to the line that we want to make, because it's exactly the line that we want to make. And so we can use that idea of the parametric equations. Remember, it was like x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct, where a, b, and c were the components of the vector that it's parallel to, and x1, y1, z1 were the points on the line. All right, so that's kind of the idea we'll use to start and get the parametric equations, and then we'll have to fiddle with it a little bit to make sure that we only get the line segment from P to Q, right? Not the entire line that connects P and Q, but just the line segment. And we'll talk about how to get that when we get there. So the first thing we want to do is find the vector that connects PQ, right? That's going to be our vector that we use to write our parametric equations, right? So again, we just do terminal minus initial. So -3 minus 1, -2 plus 6, and 5 minus 8. So if I do that, I end up getting the vector -4, +4, and -3. Right? So that is my vector, and then my point, we'll just use P, which is 1, -6, and 8. Right? So we have a vector we have that it's parallel to because it's exactly that vector, and then we have the point, so we can write the parametric equations. And again, this is from section I think 11.5 when we talked about this. Right? So x is equal to the x value, which is 1 minus 4t, y is equal to -6 plus 4t, and z is equal to 8 minus 3t. But again, what does this do? Say this is my point P in space, and this is my point Q in space. Well, what did we do? We just found this whole line that connects P and Q, right? That was what we did, because we used the vector, we used this vector that's right here, right, this vector from P to Q that's parallel to that line because it is that line, and we use this point P, and we found the equation of this big long line. But remember, that's not what we want. We really just want this line segment from P to Q, right? This happens at a certain t-value, and this happens at a certain t-value, right? Because every one of these points that's on the line happens at a certain t-value that I plug in to these x, y, z equations. So what I need to do is find the t-value that corresponds to the first point, P, and find the t-value that corresponds to the second point, Q, right? So that's the idea here. I need to, first we need to find the t, so I guess I should say what value of t gives the point P, which equals to 1, -6, 8, right? So I'm plugging t into my parametric equations right here. What value of t makes me get 1 for x, -6 for y, and 8 for z? Well, t equals to 0, right? And then what value of t gives the point Q, which is -3, -2, and 5, right? Well, that would be 1, right? So t equals to 1. So the question was to represent the line segment by a set of parametric equations. So this is my set of parametric equations, but since it was the line segment, I only want to do it for certain t values. So this is the t value from 0 to 1 is where it's going to vary. All right, so that's my set of parametric equations. Now that I have a set of parametric equations, this whole study up here, all of these definitions and stuff, and when I went ahead and drew this idea of what a vector valued function is, where I get a vector and then I just use the terminal point as the point on my curve, all this discussion was saying was that if I have a set of parametric equations and I want to write a vector valued function to represent the curve that those parametric equations represent, well, what I can do is just put the parametric equations into each component, right? So my RT would look like 1 minus 4t I plus -6 plus 4t j plus 8 minus 3t k. And I would want t to still vary from 0 to 1. So that is my vector valued function that represents the line segment from P to Q. All right, let's go ahead and end this video here. In the next video, we'll start sketching plane curves.